Milky Way, the story of our stellar home. When night falls upon Earth and the sky becomes truly dark, far from city lights, a spectacle unfolds before us that has captivated humanity throughout its entire history. Across the entire firmament stretches a hazy, luminous band, as if someone had spilled milk across the black velvet of space. This is the Milky Way, our home, our galaxy, a giant stellar island in which we live. And today we shall embark on an incredible journey through space and time to learn the history of this majestic cosmic creation. Let us begin with what the Milky Way actually is. It is a spiral galaxy containing between 200 and 400 billion stars. Try to imagine this number. If you began counting the stars of the Milky Way at a rate of 1 star per second, you would need approximately 10,000 years to finish counting. And that is still a conservative estimate. Our galaxy is so enormous that light, traveling at 300,000 kilometers per second, requires 100,000 years to cross it from edge to edge. This distance is 100,000 light years, or nearly a quintillion kilometers, a number with 18 zeros. But how did this giant stellar city come into being? To answer this question, we must return to the very beginning, to the moment of the universe's birth. Approximately 13,800 billion years ago, an event occurred that scientists call the Big Bang. At this moment, all matter, energy, space, and time itself emerged from an unimaginably dense and hot state. The first moments of the universe's existence were incredibly dramatic. Temperatures reached trillions of degrees, and space expanded at a colossal rate. In the first minutes after the Big Bang, only hot plasma existed in the universe, consisting of elementary particles. Then, as the cosmos expanded and cooled, the first atoms began to form. These were predominantly hydrogen and helium, the lightest elements of the periodic table. About 75% of ordinary matter in the universe consisted of hydrogen, 25% of helium, and only a tiny fraction was lithium and beryllium. All other elements, including carbon, oxygen, and iron, everything we ourselves are made of, appeared much later in the cores of stars. For the first several hundred million years, the universe was plunged into darkness. Astronomers call this period the cosmic dark ages. No stars yet existed, only clouds of hydrogen and helium slowly drifting through expanding space. But in the darkness, the seeds of future galaxies were already ripening. The fact is that matter in the universe is distributed unevenly. Even in the first moments after the Big Bang, tiny density fluctuations arose. Somewhere there was slightly more matter, somewhere slightly less. These microscopic inhomogeneities became the embryos of all future cosmic structures. But ordinary matter, atoms of hydrogen and helium, constituted only a small part of what determined the universe's fate. A far more important role was played by a mysterious substance we call dark matter. It does not emit light, does not absorb it, and does not interact with ordinary matter in any way known to us, except through gravity. But it was precisely dark matter, of which there is approximately 5 times more in the universe than ordinary matter, that became the architect of cosmic structures. Dark matter began to gather into clumps earlier than ordinary matter. Its gravity created a kind of well into which clouds of gas subsequently fell. Imagine invisible mountains and valleys in space, where the mountains are concentrations of dark matter. Ordinary gas, like water, flowed into these invisible depressions, accumulating there and gradually becoming denser. Thus, protogalactic clouds formed, the predecessors of future galaxies. Approximately 200 million years after the Big Bang, an epochal event occurred. The first stars ignited. They were completely unlike modern luminaries. These were giants hundreds of times more massive than our Sun, consisting exclusively of hydrogen and helium. Astronomers call them population 3 stars. These first stars burned incredibly brightly and lived very briefly by cosmic standards, only a few million years. Then they exploded as supernovae, scattering around themselves the first heavy elements synthesized in their cores. These cosmic cataclysms were simultaneously destruction and creation. The explosions of the first stars enriched the surrounding gas with elements heavier than helium and launched shock waves that compressed neighboring clouds, provoking the birth of new luminaries. Thus began the great cycle of stellar matter, which continues to this day. Each generation of stars produces more and more heavy elements, passing them on to the next generation. Approximately 13 billion years ago, when the universe was about 800 million years old, our galaxy, the Milky Way, began to form. This did not happen instantaneously or in one place. The birth of a galaxy was a long and complex process, stretched over billions of years. In several regions of space, connected by a common cloud of dark matter, clumps of gas began to condense. Each of these clumps formed its own cluster of stars, a proto-galaxy. The first stars of our galaxy were similar to their predecessors, massive, bright, and short-lived. But already the next generations contained a small admixture of heavy elements inherited from exploded giants. These population 2 stars formed in chaotically moving gas clouds, so their orbits were very diverse, elongated ellipses passing through the center of the forming galaxy at different angles. Today, these most ancient stars form what is called the halo of the Milky Way, a spherical region surrounding the flat disk of the galaxy. The age of some halo stars is nearly 13 billion years. They remember times when our galaxy did not yet exist in its present form, when instead of an ordered spiral, there was only a chaotic swarm of protogalactic fragments. By studying these ancient luminaries, astronomers can peer into the past and reconstruct the history of the Milky Way's formation. The young galaxy grew, absorbing gas from surrounding space and merging with smaller star clusters. These were not peaceful mergers. When 2 galaxies collide, their stars intermingle, orbits become distorted, and gas clouds compress, generating bursts of star formation. Throughout its history, the Milky Way has experienced many such collisions. One of the most significant mergers occurred about 10 billion years ago, when our galaxy collided with a dwarf galaxy that astronomers named Gaian Enceladus. This galaxy was approximately 4 times smaller than the Milky Way of that time, but massive enough to leave a noticeable trace. The collision lasted hundreds of millions of years. The stars of Gaian Enceladus dissolved into our galaxy's halo, and its gas replenished reserves for future star formation. Traces of this ancient merger were discovered by astronomers quite recently, analyzing the motion of millions of stars using the Gaia Space Telescope. Gradually, the chaos of the young galaxy gave way to order. Gas that had not yet turned into stars of the first generations began to settle into the plane of rotation. The fact is that a rotating cloud of matter naturally flattens. Imagine a ball of dough spinning in the air. Centrifugal force will stretch it sideways, turning it into a pancake. Something similar happened to the gas of the young Milky Way. Approximately 8 to 10 billion years ago, the thin gaseous disk of our galaxy formed. In this disk, the gas was dense enough to actively form stars. They were born no longer chaotically, but in clouds rotating together with the disk, so they inherited its ordered rotation. These population 1 stars, younger and richer in heavy elements, form the main mass of the galactic disk today. Our Sun belongs to precisely this group. The formation of spiral structure is one of the most intriguing mysteries of galactic astronomy. Why do stars and gas in the disk form elegant, winding arms rather than being distributed uniformly? The answer is connected to density waves, a kind of traffic jam on cosmic highways. Imagine a traffic jam on a ring road. Cars enter it, slow down, then exit and accelerate. The jam itself may remain in place, even though the cars in it constantly change. The spiral arms of a galaxy work on the same principle. Let us take an imaginary journey through our galaxy, beginning with its heart. The center of the Milky Way is a place where the concentration of stars reaches incredible values. If we could find ourselves there and look at the night sky, it would shine with millions of stars, many times brighter than the darkest night on Earth. Distances between neighboring stars in the central regions are measured not in light years, but in light weeks or even light days. At the very center of this stellar whirlpool lurks something truly monstrous, a supermassive black hole. Astronomers have named it Sagittarius A, pronounced Sagittarius A star. The mass of this object is about 4 million solar masses, and its size is only about 20 million kilometers in diameter. This means that if we could somehow place Sagittarius A in our solar system, it would easily fit inside Mercury's orbit while possessing a mass equal to 4 million suns. For a long time, the existence of this black hole was only a theoretical assumption. Astronomers saw that stars near the galactic center move at enormous speeds, as if circling around an invisible massive object. Some of them complete a full orbit in just a few years, accelerating to thousands of kilometers per second. Only an incredibly compact and massive object could hold them in such orbits. In 2022, the Event Horizon Telescope obtained the first image of Sagittarius A-. This was not a photograph of the black hole itself. Seeing it is impossible by definition, since even light cannot escape it. But scientists photographed its shadow against the background of glowing gas swirling around it. An orange ring with a dark spot in the middle became one of the most important images in the history of astronomy, confirming what theorists had predicted for decades. But how did this black hole come to be? This is one of the most intriguing questions of modern astrophysics. Several hypotheses exist. Perhaps it grew from a small seed. A stellar mass black hole formed during the collapse of one of the first massive stars. Over billions of years, this seed consumed gas and other stars, gradually increasing in size. Another hypothesis suggests that supermassive black holes could form directly from giant gas clouds in the early universe, bypassing the stellar stage. Whatever the history of its birth, today, Sagittarius A is relatively quiet. It consumes very little matter and radiates rather modestly compared to the active nuclei of other galaxies. But this was not always so. In the past, our black hole experienced periods of activity when more gas fell onto it and it shone brightly. Traces of one such outburst, which occurred about 3.5 million years ago, astronomers found in the form of giant bubbles of hot gas extending above and below the galactic plane. These structures, called the Fermi bubbles, are about 50,000 light years in size and are evidence of the turbulent past of the Milky Way center. Moving away from the center, we enter the bulge, a region where old reddish stars crowd so densely that they seem like a single glow. The Milky Way's bulge has the shape of an elongated bar or peanut when viewed from the side. The stars here are mainly ancient, 10 billion years old and more. They formed even before the galaxy acquired its current spiral structure. Beyond the bulge begins the disk, that same luminous band we see in the night sky as the Milky Way. The thickness of the disk is about 1,000 light years. This may seem like a lot, but in comparison with the galaxy's diameter, The disk looks like a compact disk or pancake. It is in the disk that the main mass of stars, gas, and dust is concentrated. Here, most of the galaxy's life takes place. Stars are born and die, planets form. And in one remote corner, on the third planet from a yellow dwarf, life developed that now looks at the stars and asks questions about its origins. The spiral arms of the Milky Way are true stellar nurseries. In them, gas and dust are compressed under the action of gravity and shock waves, forming giant molecular clouds. These clouds are the largest objects in the galaxy. They can contain the mass of millions of suns and extend for hundreds of light years. Inside them, temperatures drop to a few tens of degrees above absolute zero. These are the coldest places in the galaxy. When part of a molecular cloud becomes dense enough, it begins to collapse under its own gravity. This is similar to an avalanche. First slowly, then faster and faster, matter falls toward the center, heating up along the way. At the center, a protostar forms, an object that has not yet ignited thermonuclear reactions but already shines brightly due to gravitational compression. When the core temperature reaches about 10 million degrees, the synthesis of helium from hydrogen begins, and the protostar becomes a real star. But stars are rarely born alone. Usually, an entire cluster forms from a single cloud, from a few dozen to several thousand stars. Young star clusters shine with the blue light of their most massive and hottest members. These giant stars live only a few million years and then explode as supernovae. But during this short time, they manage to illuminate the surrounding nebulae, creating the breathtaking views we see in images from space telescopes. The Orion Nebula is one of the most famous examples of such a star-forming region. It is only 1,300 light years from us and is visible to the naked eye as a fuzzy spot in Orion's sword. Inside this nebula, thousands of stars are now being born, including several massive giants that illuminate the gas and make it glow pink and green. In a few million years, these young stars will disperse across the galaxy. But for now, they stay together, bound by their common origin. Open star clusters, like the one being born in the Orion Nebula, gradually disperse under gravitational disturbances from other objects in the galaxy. Over hundreds of millions of years, stars born together fly apart in different directions and lose each other. But some clusters survive much longer. These are globular clusters, dense spherical systems containing from 100,000 to several million stars. Globular clusters are true fossils of galactic history. Most of them formed during the Milky Way's birth epoch, about 12 to 13 billion years ago. Their stars are poor in heavy elements and have the reddish color characteristic of old luminaries. About 150 globular clusters are known in the Milky Way, most of which orbit the galaxy in its halo, far from the disk plane. The study of globular clusters helped astronomers understand the true dimensions of our galaxy. At the beginning of the 20th century, American astronomer Harlow Shapley discovered that globular clusters are not distributed randomly, but concentrate toward one region of the sky, in the direction of the constellation Sagittarius. He correctly concluded that the center of the galaxy lies in this direction, and the Sun is located far on its periphery. Before this, many scientists believed that the Sun was near the center of the Milky Way. Beyond the visible boundary of the disk extends an invisible halo of dark matter. We cannot see it directly, but its presence betrays itself through gravity. Stars at the edges of the galaxy move faster than they should if only visible matter were attracting them. This means there must be something else there, invisible mass that holds these stars in their orbits. The dark matter halo extends much farther than the stellar disk, possibly 600,000 light years or even more, and contains 10 times more mass than all the stars of the galaxy combined. The nature of dark matter remains one of the greatest mysteries of modern physics. We know it exists, we can measure its gravitational influence, but we do not know what it consists of. The most popular hypothesis suggests that it is some unknown elementary particles that practically do not interact with ordinary matter. Physicists around the world build detectors in deep underground laboratories, hoping to catch these elusive particles, but so far without success. The Milky Way is not alone in space. Our galaxy is part of what is called the Local Group, a cluster of more than 80 galaxies bound by mutual gravity. The largest member of the group is the Andromeda Galaxy, a spiral galaxy slightly exceeding the Milky Way in size and mass. Andromeda is approximately 2.5 million light-years from us and is the most distant object that can be seen with the naked eye under good conditions. The two large spirals are accompanied by many dwarf galaxies, small systems containing from a few million to several billion stars. The most famous satellites of the Milky Way are the Large and Small Magellanic Clouds, visible in the southern hemisphere as hazy luminous patches. They are approximately 160,000 light-years from us and are gradually approaching our galaxy. In the future, the Milky Way will probably absorb them, as it has already absorbed many of its neighbors in the past. But the most dramatic event in the future of our galaxy is connected not with dwarfs, but with a giant. The Andromeda Galaxy is approaching the Milky Way at a speed of about 110 kilometers per second. In 4 to 5 billion years, the two spirals will collide, beginning a grand cosmic dance that will last billions of years. The stars of both galaxies will intermingle, the spiral structure will be destroyed, and ultimately a new giant elliptical galaxy will form, which astronomers have already dubbed Milky. This collision may seem like a catastrophe, but in reality, for individual stars and planets, it will be almost imperceptible. Distances between stars and galaxies are so vast that the probability of a direct collision between two luminaries is negligibly small. Even when our solar system finds itself at the epicenter of the merger, the nearest star will still be light years away from us. The main change will concern the night sky. It will become incredibly beautiful when billions of stars from both galaxies fill the firmament. However, by that time, there will hardly be anyone on Earth to admire this spectacle. In about 1 billion years, our sun will become so hot that the oceans will evaporate, and in a few more billion years, it will turn into a red giant, swallowing Mercury and Venus and turning Earth into a scorched desert. But that is an entirely different story. Let's return to the present and talk about how humans discovered and studied the Milky Way. The history of this knowledge is one of the most fascinating chapters in the history of science. Ancient people saw the same luminous band in the sky that we do, but explained it differently. The Greeks called it Galaxias Kyklos, the Milky Circle, and connected it with the myth of the goddess Hera, whose milk spilled across the sky. Hence comes our word galaxy. The Romans translated the Greek name as Via Lactea, the Milky Way, which gave us the Russian name Milky Way. In other cultures, this celestial object received no less poetic names: the Celestial River in China, the Bird's Path in Finland, the Straw Path in some Slavic traditions. But what is this luminous band actually? The first person to give a scientific answer to this question was Galileo Galilei. In 1610, he pointed his primitive telescope at the Milky Way and discovered that the hazy glow breaks up into many individual stars, too dim to distinguish with the naked eye. This was the first proof that the Milky Way is not a celestial river or spilled milk, but a cluster of an unimaginable number of stars. The next important step was made by English astronomer William Herschel at the end of the 18th century. He systematically counted stars in different parts of the sky, trying to determine the shape of the stellar system. Herschel concluded that the Sun is inside a huge flattened cluster of stars, resembling a millstone in shape. This was the first scientific description of our galaxy's structure, although Herschel mistakenly believed that the Sun was near its center. The question of the size of the galaxy and the Sun's position within it remained open until the 20th century. The problem was that interstellar dust absorbs and scatters light, preventing us from seeing distant regions of the galaxy. Looking along the plane of the disk, we see only the nearest few thousand light years. Beyond that, everything is hidden by a dust veil. This created the illusion that stars were distributed approximately uniformly around the Sun. The situation was changed by the study of globular clusters and a special type of variable stars, Cepheids. Cepheids periodically change their brightness, and the pulsation period is directly related to the star's true luminosity. By measuring the period and apparent brightness of a Cepheid, one can calculate the distance to it. This method, discovered by American astronomer Henrietta Leavitt in 1908, became the key to measuring cosmic distances. Using Cepheids, Harlow Shapley in 1918 determined distances to globular clusters and showed that the center of their distribution is not in the Sun, but in the direction of the constellation Sagittarius, approximately 50,000 light-years from us. Modern measurements have refined this distance to 26,000 light-years, but Shapley's main conclusion proved correct. The Sun is located far on the periphery of a huge stellar system. But is our galaxy the only one in the universe, or do other similar systems exist? This question was one of the most debated in astronomy at the beginning of the 20th century. Some fuzzy spots in the sky, so-called spiral nebulae, looked like miniature versions of the Milky Way. But how far away are they? If they're inside our galaxy, then they're simply gas clouds. If they lie far beyond its boundaries, then they are separate stellar systems comparable in scale to the Milky Way. The answer was given by American astronomer Edwin Hubble in 1924. Using the largest telescope of that time, the 100-inch reflector of Mount Wilson Observatory, he discovered Cepheids in the Andromeda Nebula and measured the distance to it. It turned out to be enormous, about 1 million light-years. Modern measurements give 2.5 million. This was much larger than the size of the Milky Way, which meant that the Andromeda Nebula is a separate galaxy, just as enormous as our own. The universe suddenly became immeasurably larger. Since then, astronomers have discovered hundreds of billions of galaxies scattered across the universe for billions of light-years. They unite into groups and clusters. Clusters form superclusters, and superclusters line up into giant filamentary structures separated by colossal voids. This entire grand picture resembles foam or a sponge, where the walls of bubbles are galaxies and the interiors of bubbles are almost empty space. The Milky Way occupies a modest place in this cosmic hierarchy. Our local group is part of the larger Virgo cluster, which in turn is part of the Laniakea supercluster. The name means immense heaven in Hawaiian. Laniakea extends for 500 million light-years and contains about 100,000 galaxies. And this is only a tiny fragment of the observable universe. The study of our galaxy continues today, and technology makes it increasingly detailed. The Gaia Space Telescope, launched by the European Space Agency in 2013, has measured the positions and motions of nearly 2 billion stars in the Milky Way. This has allowed the creation of the most detailed three-dimensional map of our galaxy. Gaia's data has revealed many amazing structures, remnants of absorbed dwarf galaxies, waves in the stellar disk, streams of stars moving in unusual orbits. One of Gaia's most intriguing discoveries is the detection of signs that our galaxy is still digesting the consequences of ancient collisions. Stars that once belonged to absorbed galaxies retain their characteristic motions and chemical composition even after billions of years. By studying these cosmic fossils, astronomers are reconstructing the history of the Milky Way's formation step by step. Infrared telescopes, such as the James Webb Space Observatory, allow us to peer through the dust veil and see regions of the galaxy hidden from ordinary optical telescopes. They reveal the structure of the Milky Way's central regions, explore star-forming regions hidden in dark molecular clouds, and study the most ancient stars of the halo. Radio telescopes add another dimension to our understanding of the galaxy. Radio waves pass through dust unimpeded, allowing us to map the distribution of hydrogen, the main component of interstellar gas. Radio observations revealed the spiral structure of the Milky Way long before it could be seen in the optical range. They also helped discover and study the black hole at the center of the galaxy. Neutrino and gravitational wave detectors open entirely new windows into the universe. Neutrinos, ghostly particles that hardly interact with matter, carry information from the most extreme regions of the cosmos, including the cores of collapsing stars. Gravitational waves, ripples in the fabric of space-time, are born during collisions of black holes and neutron stars. These new observational methods promise revolutionary discoveries in understanding our galaxy. Now let us talk about what place the solar system occupies in this grand picture. Our planetary system is a tiny grain of sand in the ocean of the Milky Way, but its location has proven surprisingly favorable for the development of life. The Sun is located approximately 26,000 light-years from the center of the galaxy, in a relatively quiet region of the disk. We are positioned between two main spiral arms, the Perseus arm on the outside and the Sagittarius arm on the inside. Our small Orion arm is sometimes called a spur or branch of the Sagittarius arm. This location has important consequences. Near the galactic center, the density of stars is so high that planetary systems would constantly be subjected to gravitational disturbances from passing luminaries. Comets and asteroids would be knocked from their orbits, bombarding the inner planets. Intense radiation from numerous stars and periodic supernova flashes would create a hostile environment for complex biological molecules. On the outer edges of the galaxy, there are different problems. There are few heavy elements there necessary for the formation of rocky planets like Earth. Stars are born there less frequently, meaning fewer opportunities for the emergence of planetary systems. Our position, far enough from the dangerous center, but not so far as to suffer from a deficit of materials, seems optimal for the development of life. Some scientists call this region the galactic habitable zone. The Sun completes one orbit around the galactic center in approximately 220 million years. This value is sometimes called a galactic year. During the existence of the solar system, about 4.5 billion years, the Sun has completed about 20 such orbits. When dinosaurs roamed the Earth, the Sun was on the opposite side of the galaxy from its current position. During its journey around the galaxy, the solar system crosses different regions, sometimes passing through spiral arms with their clouds of gas and dust, sometimes through calmer interarm spaces. Some scientists suggest that these transitions could have affected Earth's climate and even the evolution of life, although the evidence for this hypothesis remains indirect. The nearest star to the Sun is Proxima Centauri, a red dwarf located approximately 4 light-years from us. It is part of the triple star system Alpha Centauri, which also includes 2 Sun-like stars, Alpha Centauri A and Alpha Centauri B. Proxima has been found to have a planet roughly Earth-sized, orbiting in the potentially habitable zone of its star. This is the nearest exoplanet to us, and it is of enormous interest as a possible target for interstellar exploration in the distant future. Within a radius of 20 light-years from the Sun, there are about 100 stars. Most of them are dim red dwarfs, much smaller and cooler than our Sun. These stars are so faint that they cannot be seen with the naked eye, but they constitute the majority of the galaxy's stellar population. For every star like the Sun, there are dozens of red dwarfs. Red dwarfs live incredibly long. The smallest of them will shine for trillions of years, thousands of times longer than the current age of the universe. When all massive stars have long since died out, red dwarfs will continue to smolder like embers in a cooling cosmic fire. Planets around such stars could exist practically forever by human standards. But let us return to larger scales. As we have already said, the Milky Way is only one of hundreds of billions of galaxies in the universe. And here an amazing question arises. If there are so many galaxies, why do we not hear signals from extraterrestrial civilizations? This question, known as the Fermi paradox, has no definitive answer. Perhaps life is extremely rare in the universe. Perhaps intelligent life destroys itself before it can announce itself at the galactic level. Perhaps aliens exist but do not wish to communicate with us or use means of communication that we are unable to detect. Or perhaps the galaxy is full of life and we're simply looking in the wrong place or do not know how to look properly. The search for extraterrestrial intelligence continues. Radio telescopes listen to the sky, hoping to catch an artificial signal. Spacecraft search for signs of life on other bodies of the solar system, on Mars, on the moons of Jupiter and Saturn. Telescopes analyze the atmospheres of exoplanets, searching for biomarkers, gases that could indicate the presence of life. Even if we turn out to be alone in the Milky Way, this does not diminish the grandeur of our galaxy. Perhaps it is we who are destined to populate it. Humanity has already taken its first steps into space, visited the moon, sent robots to Mars and the outer planets, launched spacecraft that are now leaving the solar system. Millennia will pass, and perhaps our descendants will spread among the stars of the Milky Way, creating new civilizations on planets near distant suns. And now, let us examine in more detail the stellar population of our galaxy, those inhabitants that make the Milky Way a living and dynamic place. Stars differ in size, mass, temperature, brightness, age, and chemical composition. The hottest and most massive of them, blue giants and supergiants, are tens of times heavier than the Sun and shine millions of times brighter. They are very rare, but so conspicuous that they dominate the light of the spiral arms. Rigel in the constellation Orion is an example of such a supergiant. It is 800 light-years from us, but is one of the brightest stars in the night sky. At the other end of the scale are red dwarfs, stars with less than half the Sun's mass. They're so dim that the nearest red dwarf to us, Proxima Centauri, is invisible without a telescope, despite its proximity. But it is red dwarfs that constitute about 70% of all stars in the galaxy. They are inconspicuous but numerous. Between these extremes lies the main mass of stars. Yellow dwarfs like our Sun, orange dwarfs slightly smaller in size, white stars, red giants in the late stages of evolution. Each class of stars tells its own story. A star's life is determined primarily by its mass. Massive stars live fast and bright, burning through their fuel in a few million years. Low-mass stars are economical and long-lived, lasting for trillions of years. Our Sun is somewhere in the middle. It is about 4.5 billion years old, and it has roughly the same amount of time left to exist in its current form. In the core of every star, thermonuclear fusion occurs, a process in which light atomic nuclei merge into heavier ones, releasing energy. In stars like the Sun, hydrogen transforms into helium. More massive stars are capable of synthesizing even heavier elements: carbon, oxygen, neon, up to iron. Elements heavier than iron form only during supernova explosions and neutron star mergers. In these catastrophic events, gold, platinum, uranium, and all other heavy elements are created. This means that every atom in our body was once created in the core of a dying star. The carbon in our cells, the oxygen in the air, the iron in our blood, all of this is stardust. We are literally made from stellar material. And when we look at the Milky Way, we are looking at our ancestry. When a star exhausts the hydrogen fuel in its core, its death throes begin, a dramatic series of transformations that ends in one of several possible finales. Stars like the Sun first swell into red giants, swallowing the nearest planets. Then their outer layers fly off into space, forming a beautiful planetary nebula, while the core contracts into a white dwarf, an object the size of Earth, but with the mass of the Sun, white dwarfs gradually cool over billions of years, turning into cold, dark objects. Massive stars, in their lives, far more spectacularly. When iron accumulates in their cores, thermonuclear fusion ceases. Fusing iron nuclei requires more energy than is released. The core suddenly collapses under its own gravity, and the outer layers crash down onto it and bounce off, generating a colossal explosion, a supernova. For a short time, a supernova can shine brighter than the entire galaxy in which it erupted. After a supernova explosion, either a neutron star remains, an object the size of a city but with the mass of the Sun, or a black hole if the original star was massive enough. Neutron stars rotate at enormous speeds, up to several hundred revolutions per second, and possess incredibly powerful magnetic fields. Some of them emit narrow beams of radio waves which, like lighthouse beams, periodically pass through Earth. We call such objects pulsars. The Milky Way contains about 1 billion neutron stars and, by various estimates, from 100 million to 1 billion stellar mass black holes. Most of them are invisible. Black holes do not emit light, and neutron stars are too dim. But sometimes they reveal themselves when they collide with each other or when they consume matter from a neighboring star. In 2017, gravitational wave detector for the first time recorded the merger of two neutron stars in the galaxy NGC 4993, located 130 million light-years from us. This event was accompanied by a burst of gamma radiation and afterglow across all ranges of the electromagnetic spectrum. Astronomers were able to observe how heavy elements are synthesized during the collision, direct confirmation of the theory of the origin of gold and other rare elements. Similar events occur in our galaxy as well, though much less frequently than supernova explosions. In the last 1,000 years, several supernovae visible to the naked eye have been recorded in the Milky Way. The most famous of them is the supernova of 1054, whose remnant we now see as the Crab Nebula. Another famous supernova flared in 1572 and was described by Danish astronomer Tycho Brahe. The last supernova in our galaxy visible to the naked eye occurred in 1604. It was observed by Johannes Kepler. More than 400 years have passed since then, and astronomers eagerly await the next nearby supernova. Statistics suggest that supernovae should erupt approximately once every 50 years in a galaxy like the Milky Way, but many of them are hidden from us by dust clouds. The next visible supernova could flare at any moment, tomorrow or in a century. One of the candidates for the role of the next supernova is Betelgeuse, a red supergiant in the constellation Orion. This star is already in the final stages of its evolution and will explode within the next 100,000 years, perhaps even in our lifetime. When this happens, Betelgeuse will become brighter than the full moon and will be visible even in daylight for several weeks. Between the stars of the Milky Way extends the interstellar medium, the rarefied gas and dust filling the space of the galaxy. This medium is far from uniform. In some places, it is almost empty, only a few atoms per cubic centimeter, billions of times more rarefied than the best vacuum achievable in earthly laboratories. In other places, gas gathers into dense clouds, where thousands or even millions of particles occupy the same volume. Interstellar gas consists predominantly of hydrogen, about 70% by mass. Another approximately 28% is helium, and only about 2% consists of heavier elements. These proportions reflect the primordial chemical composition of the universe, slightly enriched by the products of stellar nucleosynthesis over billions of years. Interstellar dust consists of tiny particles the size of microns and smaller, made of silicates, carbon, and ices. Dust constitutes only about 1% of the mass of interstellar matter, but plays an enormous role in the life of the galaxy. It absorbs and scatters light, making distant regions of the galaxy inaccessible to optical observations. It serves as a catalyst for chemical reactions in space. Complex molecules form on its surface, and it is building material for planets. Solid particles and circumstellar disks stick together, gradually growing to the size of asteroids and planetesimals. In the cold, dense clouds of interstellar gas, many complex molecules have been found, more than 200 different types. Among them are water, ammonia, formaldehyde, methanol, ethyl alcohol, acetic acid, and even the simplest amino acids, the building blocks of proteins. Space has turned out to be a true chemical laboratory where organic compounds are synthesized, which can then reach the surfaces of planets along with comets and meteorites. Hot, rarefied gas fills what are called superbubbles, giant cavities in the interstellar medium blown out by a series of supernova explosions. Our solar system is inside one such bubble, called the local bubble. Its diameter is about 300 light years, and inside there is almost no cold gas or dust. It is believed that this bubble formed several million years ago when several massive stars exploded in its vicinity. Cosmic rays, high-energy particles, mainly protons and atomic nuclei, are also part of the interstellar medium. They are accelerated in shock waves from supernovae and permeate the entire galaxy, sometimes reaching Earth. Cosmic rays play an important role in the chemistry of interstellar gas and can affect the climate of planets. The magnetic field of the galaxy, although very weak by earthly standards, approximately 100,000 times weaker than Earth's magnetic field, encompasses the entire Milky Way and structures the interstellar medium. Magnetic field lines align dust particles, creating characteristic polarization of light from distant stars. They direct the motion of cosmic rays and influence the formation of stars in molecular clouds. All of this, stars, gas, dust, magnetic fields, cosmic rays, forms the complex ecosystem of the galaxy, where each component influences the others. Supernova explosions enrich the gas with heavy elements and compress clouds, provoking the birth of new stars. Young stars ionize surrounding gas with their radiation and disperse clouds with stellar winds. Old stars return matter to the interstellar medium, closing the cycle. This galactic ecology has been functioning for 13 billion years and will continue for many billions more. But what does the Milky Way look like from the outside? We cannot go beyond the boundaries of the galaxy to photograph it, so scientists have to reconstruct its appearance from indirect data. Observations of the distribution of stars, gas, and dust, measurements of their motion speeds, comparison with other spiral galaxies. All this allows us to compose a picture of how the Milky Way would look to a hypothetical external observer. If we could look at our galaxy from above, we would see a magnificent spiral with a bright central bar and two main arms winding around it. The diameter of the stellar disk would be about 100,000 light-years, but if we account for gas and dark matter, the galaxy size would be even larger. The disk's color would be bluish-white, with pinkish spots of nebulae and dark streaks of dust lanes. The central bulge would glow yellowish-orange. This is the color of old stars. If we looked at the galaxy from a side, it would appear as a thin, luminous disk with a thickening in the middle. That same bulge. The thickness of the disk would be about 1,000 light-years, only 1% of its diameter. This ratio is approximately like a stack of a few sheets of paper with a diameter of 1 meter. Above and below the disk plane, we would see scattered globular clusters, small bright spheres orbiting the galaxy at great distances. And even farther, invisible to the eye, clouds of dark matter would extend, enveloping the galaxy in a giant invisible cocoon. Now let us talk about what awaits the Milky Way in the future. The galaxy is not static. It lives, changes, evolves. And although galactic time flows slowly by human standards, change is inevitable. In the near future, by cosmic standards, the Milky Way will continue to absorb its dwarf satellites. The large and small Magellanic Clouds, currently located approximately 160,000 light-years away, are gradually approaching our galaxy. In a few billion years, they will be completely absorbed. Their stars will dissolve among the stars of the Milky Way, and their gas will go toward forming new luminaries. A more dramatic event will occur in approximately 4.5 billion years. The collision with the Andromeda Galaxy. Andromeda is now 2.5 million light-years from us, but it is approaching at a speed of about 110 kilometers per second. Both galaxies are attracted to each other by the force of mutual gravity, and their encounter is inevitable. A galaxy collision is not an instantaneous catastrophe, but a long process stretched over billions of years. First, the galaxies will approach, deforming each other with tidal forces. The spiral arms will stretch and curve, and long stellar streams will be ejected from both galaxies. Then the galaxies will pass through each other, separate, approach again, and this dance will continue several times until finally both systems merge completely. The result of the merger will be a giant elliptical galaxy. The spiral structure will be completely destroyed. Stellar orbits will become chaotic, and the ordered rotation of the disk will give way to disordered motion in different directions. Gas from both galaxies will collide and compress, causing a burst of star formation. Billions of new stars will ignite within a few 100 million years after the merger, and then star formation will gradually fade as all the gas is consumed. The two supermassive black holes, our Sagittarius A and its counterpart at the center of Andromeda, will also eventually merge. This process will be accompanied by powerful gravitational wave emission, which will carry away an enormous amount of energy. The combined black hole will be even more massive than the sum of the masses of the two original ones. If by that time there are still intelligent beings on Earth or in its vicinity, or if our descendants have spread among the stars, they will witness an incredible spectacle. Andromeda in the sky will grow and grow, transforming from a small fuzzy spot into a giant luminous structure occupying half the sky. And then the entire sky will fill with stars, native and foreign, mixed together in a grand cosmic dance. But even this merger is not the end of the story. On even longer timescales, galaxies will continue to change. Red dwarfs, which constitute the majority of the stellar population, will slowly burn out, dimming over trillions of years. White dwarfs will cool, turning into cold, dark objects. Occasionally, stellar collisions and ejections into intergalactic space will gradually reduce the galaxy's mass. In trillions of years, most stars will die out. The galaxy will consist mainly of dead remnants, white dwarfs, neutron stars, black holes, scattered through almost empty space. This will be the dark era in cosmic history, when the light of stars will remain only a memory. But even this is not the very end. On timescales of quintillions of years, numbers with 18 zeros, even protons may decay if certain theories of particle physics are correct. Ordinary matter will gradually dissolve, leaving only black holes, which will slowly evaporate through Hawking radiation. And at the very end, after an unimaginable number of years, even black holes will evaporate, leaving only scattered radiation in an infinitely expanding universe. But let us not end on such a gloomy note. After all of this is an unimaginably distant future, separated from us by spans of time that are difficult even to comprehend. Right now, the Milky Way is full of life. Stars are born and die, planets circle their suns, and on one of these planets, intelligent beings look at the night sky and try to understand their place in the universe. The Milky Way is our home, our homeland in space. We are one with it. The atoms of our bodies were forged in the stars of the galaxy. We rotate together with it around an invisible center. We are part of this grand stellar island. And when we look at the hazy, luminous band in the night sky, we are looking at ourselves from within. The history of the Milky Way is a history of 13 billion years of cosmic evolution. From the first clumps of gas in the dark young universe to the magnificent spiral galaxy we see today. From the first massive stars that illuminated the cosmic darkness to our modest sun with its tiny blue planet. This is the story of the creation of the elements from which we are made, the story of the formation of the world in which we live. And this story continues. Every second in our galaxy, new stars are born and old ones die. Every second, planets revolve around their luminaries and comets fly through interstellar space. Every second, the Milky Way changes slightly, imperceptibly to us, but inexorably. We live in a dynamic, evolving system, and we ourselves are part of it. Looking at the night sky, we see not just a beautiful picture, we see history. Light from distant stars has traveled to us for thousands and even millions of years. When we look at the center of the galaxy, we see it as it was 26,000 years ago, when our ancestors painted mammoths on cave walls. When we look at Andromeda, we see it as it was 2.5 million years ago, when the first representatives of the genus Homo walked the African savannas. Astronomy is a time machine. By studying distant galaxies, we peer into the past of the universe, into epochs when neither Earth, nor the Sun, nor even the Milky Way in its present form existed. And by studying our own galaxy, we trace the history that led to the emergence of ourselves. Humanity is the Milky Way's way of knowing itself. Stardust that has gained consciousness and asked the question of its own origin. And every time we learn something new about our galaxy, about its structure, history, fate, we learn something new about ourselves. So the next time the night is dark enough and the sky clear enough, find a place far from city lights and look up. Find that hazy, luminous band that crosses the firmament from horizon to horizon. This is the Milky Way, hundreds of billions of stars, each with its own history, each potentially surrounded by planets. This is our home in the universe, our stellar island in the midst of the endless cosmic ocean. And remember, You are not merely looking at the Milky Way. You yourself are part of it. The atoms of your body were forged in the cores of dead stars and scattered by supernova explosions billions of years ago. You are a child of the galaxy, its creation and its consciousness. In a sense, when you look at the stars, the galaxy is looking at itself. This is an amazing thought, is it not? We are not separated from the cosmos. We are not strangers in this universe. We are an integral part of it. The carbon in our cells, the oxygen in our lungs, the calcium in our bones, the iron in our blood, all of this was created in the thermonuclear furnaces of stars and spread across the galaxy by explosions and stellar winds. We're literally made of stellar matter. And now, after 13 billion years of cosmic evolution, this stellar matter has gained the ability to be aware of itself, to ask questions, to seek answers. We are the universe's way of knowing itself. What an amazing privilege to be part of this grand process. Science has come a long way from Galileo's first telescopic observations to modern space observatories. We have learned an incredible amount about our galaxy, its structure and dimensions, the history of its formation, its population of stars and planets, the chemical composition of the interstellar medium, the nature of dark matter and black holes. But even more mysteries await their solution. Where did dark matter come from, and what is it made of? How are the first stars and galaxies formed? Are we alone in the Milky Way, or does other intelligent life exist somewhere among its hundreds of billions of stars? What is the true origin of supermassive black holes? These and many other questions face modern astronomy, and the answers to them may reveal even more astonishing truths about the nature of our cosmic home. Humanity is at the beginning of a great journey of space exploration. We have already visited the moon, sent robots to other planets of the solar system, launched spacecraft beyond its boundaries. Perhaps one day our descendants will travel to other stars, colonize planets near neighboring luminaries, spread throughout the entire Milky Way. This is a bold dream, but is it not from bold dreams that progress is born? For now, we remain on our small blue planet, circling a yellow dwarf on the outskirts of a spiral galaxy. But this is no reason for despondency. On the contrary, it is a reason for reverence and wonder. We live in an incredible universe, full of wonders and mysteries. And one of the greatest wonders is that we are capable of recognizing this grandeur and marveling at it. The Milky Way will exist for many billions of years after our sun dies out and Earth disappears. Stars will be born and die. The galaxy will merge with Andromeda. Entire epochs of cosmic history will pass. But while we are here, while we look at the stars and ask questions, the story continues. And who knows what discoveries await us ahead? What secrets of the galaxy we are yet to uncover? What new horizons will open before humanity? One thing can be said for certain. The history of the Milky Way is our history too. We are inseparably connected to our galaxy by bonds of atoms and gravity, of light and time. And as long as at least one intelligent gaze is turned to the night sky, as long as at least one mind strives to understand the universe, this connection will not be broken. So look at the stars, study them, marvel at them, for they are distant relatives, your cosmic ancestors. And the Milky Way is your home, the only island known to us in the universal ocean where life arose and where, perhaps, it is destined to flourish more brightly than ever before. The history of our galaxy has already lasted 13 billion years. But in a sense, it is only just beginning because now there is someone to tell it, someone to hear it and understand. And every time we turn our gaze to the night sky, we add a new chapter to this endless story, a chapter written by the light of distant stars and humanities striving for knowledge. such as the history of the Milky Way, the history of our stellar home, told from the Big Bang to the present day and beyond into an unimaginably distant future. A history majestic and grand, a history intimate and personal, because it directly concerns each of us. We are all children of the galaxy, heirs to 13 billion years of cosmic evolution. And the awareness of this fact can change our view of the world and our place in it. After all, what could be more inspiring than the realization that you are part of something so enormous and beautiful as the Milky Way? That the atoms of your body remember times when there was neither Earth nor sun? That you are connected by invisible threads to all the stars of the galaxy, past, present, and future? Perhaps this sense of cosmic unity is the main lesson that the Milky Way teaches us. A lesson that we are not alone in the universe, not in the sense of aliens, but in the sense that we are part of a great whole, part of a majestic cosmic process that began long before us and will last long after. And the awareness of this connection, this belonging to something greater, perhaps this is one of the main values that the study of stars gives us. So may the Milky Way always remind us of our place in the universe, modest and grand at the same time. May its light, traveling for millennia, reach our eyes and our hearts, awakening curiosity, reverence, and the desire to learn more. Because in this striving lies the essence of what it means to be human, a being that looks at the stars and asks, why? And the Milky Way, our galaxy, our home, answers with billions of lights twinkling in the night.